Hi everyone, welcome to the AstroLaunch podcast. I'm your host Amy, and today I'm excited to be joined by Daniel Mayerson, a theoretical physicist whose research focuses on black holes, gravitational waves, and some of the biggest mysteries on our universe. Hi, Mr. Mayerson, welcome to the podcast. It's so good to have you here.
I'm glad to be here. Thanks.
So, to start off, can you please tell us a little bit about yourself and your job?
Sure. So I'm Daniel Mayerson. I'm currently, yeah, my job is a little bit complicated. So let me tell you a little bit about that. So I'm currently the institute coordinator at the Leuven Gravity Institute, which is sort of an interdisciplinary institute surrounding everything around gravity, gravitational waves, gravitational wave detectors, instrumentation, etc. At the KU Leuven at the university in Belgium. And so my role there is basically to coordinate the institute. There's two other institute coordinators, and together we try to bring everybody together, which across disciplines can be very challenging. Um, that's one of my jobs at the moment. And so at the moment, I'm also part-time a member of the ET Flanders, so Einstein Telescope Flanders team. So basically, the team that's behind trying to get the Einstein telescope to our region. So Einstein telescope is a future gravitational wave detector. I guess we'll talk more about that later. And so I'm in that team for science communication and outreach. So yeah, a lot of all over the
That's really
place. Yeah.
interesting. Yeah. So, what first sparked your interest in like physics and astronomy?
Um, so I think, so I'm a theoretical physics physicist by training, and I think my interest in theoretical physics, high energy theoretical physics to be more precise, is that I was just always interested in how things work, but not just superficially, like at a fundamental level, right? I really want to know what's sort of the basic building blocks of the universe, of everything, how does everything work? And why, if we even dare ask the question why do things work the way that they do? And that kind of drove me towards high energy physics is basically saying, okay, how small can we go? What are the fundamental building blocks of nature, the fundamental particles? How do they interact? Why isn't it a different way? Can we understand the universe from very first principles? So that's kind of what drove me towards where I am.
So, when you were in high school, did you like already know that you want to pursue like a career in science, or did that develop later on?
That's an interesting question because I just said, I was really driven to, knowing everything at its most fundamental level, but that was true in high school as well. Like I was very interested in these kind of topics, and I read a lot of popular scientific books on physics and theoretical physics. But my actual first idea of career was more in computer science. So I wanted to be a programmer. And at the end of high school, I was very much, oscillating between I want to do physics, theoretical physics, or maybe math, because, it's also kind of a fundamental building block, or, I want to do computer science and become a programmer. And so in the end, I chose physics. Of course, the other careers would have been very interesting as well, because of this, fundamental thirst sort of for understanding the universe.
So, what was your educational journey from a student to a theoretical physicist?
So you mean like what's my path in
Yeah,
university and everything?
probably, yeah.
Yeah. Um, so I went after high school. I went to study here in Leuven in Belgium. I did a bachelor and a master here. So here, as opposed to the US, you don't do a bachelor of arts where you do a lot of different courses. Here you choose. I start in the bachelor of physics, and so that means that I get 3 years of physics and mostly just physics. Um, so I did bachelor and master in physics, and then I went to Cambridge for a year as well. I did an additional master in theoretical physics there. It's called Master of Advanced Studies, or Part Three. It's also known as. And then after that, so that was basically, like more knowledge, more very specifically theoretical physics, high energy physics, the stuff that I really wanted to work in. And then I did my PhD in Amsterdam, so Amsterdam University, and there I started working on, the topics that interest me now still, which is basically black hole physics. And sort of how to understand black holes in string theory and quantum gravity, that kind of topic. After my PhD, I moved around a lot as a postdoctoral researcher. So I went to Michigan first, University of Michigan. Then I went to Saclay, so the research institute there in Saclay in France, close to Paris. And then I was also a postdoc in Leuven before I transitioned into being the institute manager there. So as is typical in my field of theoretical physics, I did a lot of moving around before, luckily finding a sort of a permanent job.
That's like a really interesting journey. And like the reason I asked that question was because a lot of students wonder how to actually
Mhm.
get to some place with that they want to be. And so it's always like really interesting to hear about every podcast, how people actually get to where they become. And it's really, I like to hear about everyone's journey. So
Yeah.
yeah. So now we're gonna dive into like your research and like the work you've been doing.
Well,
So
if you don't mind, since you said this is very interesting for high school students, sorry to interrupt you,
no, it's okay.
but I'd very much like to give a piece of advice at this point, right?
Yeah.
Because like I said, I moved around a lot,
Yeah.
doing research in different places, and something we see not necessarily in high school students, but certainly on at every level, right? Whether it's master students going into PhD, PhD students going for postdocs, postdocs going for another postdoc, et cetera, is, you know, the most important thing is not, to do the thing that is the best on your CV or whatever, or, that you think will give you the highest chances to succeed or whatever. No, the most important thing is to do something that you're really passionate about and that you enjoy doing, right? That's always the advice that we give to our PhD student or master students, even when they ask, like, maybe I should do a PhD. We always say, look, if you really want to do it, if that's something you really want to do, then do it, right? But don't do it because you think that's the best career thing
Yeah.
to do. And all of this is hard, right? It's hard to do a PhD. It's hard to do a postdoc. It's hard to move around a lot. That's certain sacrifices that you have to be comfortable with because you're so passionate about doing your research. So try to keep that in mind. I would say, to everybody, that's really the most important thing is to do something that you're passionate about and that you like.
No, I really like that advice because even now, high school students always strive to do the one thing that will look good on their college apps.
Yes.
Same with college application, and it's
Yes.
important to realize that you should do something that you actually want to do and are passionate about, rather than just
Yes,
doing it for it to
absolutely.
look good. Yeah.
Absolutely.
Okay, so now we're gonna dive into like your research and what you've been doing today. So for
Sure.
students who may not be like familiar, what exactly is a theoretical physicist?
Yeah. So, I mean, there's a lot of different flavors of theoretical physicists, let's say, right? It's a very broad concept, and there's people like me, but there's also people who do a lot more, simulations and computations. And there's also different subject areas. So specifically, what I am is I'm a theoretical high energy physicist. So that means that I do things like string theory, quantum gravity. That's the kind of things that I'm interested in. This is very mathematical physics, right? So basically, you know, in some places we're in the applied maths department, right? People like me. And the reason is because, string theory is basically applied maths at this point, right? We don't really have any testable predictions, right? That's a whole nother subject by itself. But, so basically what I do is I try to do some kind of calculation within string theory or within some, toy model that I think represents string theory, to understand how string theory, if it is really a theory of everything, if it is really a consistent theory of gravity, of quantum gravity, how it would predict, what happens inside of a black hole, for example, right? Because that's a big mystery. How does it resolve certain things that we don't understand yet, right? How does it increase our understanding about sort of the fundamental way that things work? So very, very specifically, what I do is what does a day look like for me if I'm doing research? Because in my current roles, I'm doing a lot of organizing and coordinating, which is not really research. Is basically calculations, right? So a lot of analytical calculations, pen and paper, or I use computer programs like Mathematica, which is basically a package that allows you to do symbolic calculations. Sometimes I do some numerical simulations too, right? Like maybe I have some equations that are just too hard to solve or too hard to simulate what they're actually telling me. And so then I do try to do that. And then in the end, the end result is trying to get a nugget of insight or information about whatever problem I'm thinking of, right? So maybe it helps to talk about what I'm currently
Yeah.
thinking of in research. So like I said, I'm a theoretical high energy physicist by training, meaning I come from string theory. So I've been trained in string theory, and in particular, black holes and string theory. How do they behave? Um, so string theory basically tells you, look, general relativity, like Einstein predicts, is a very good theory, but there are corrections to it, right? It's not the end of the story. And so, of course, I think it, a good question to ask then is, okay, but these corrections, these deviations from what Einstein predicts, is that something you can actually go and measure or see in real life? Um, and even though that's a very logical question, it's not a question that's asked a lot by string theorists, right? They often stay in their mathematical sandbox. And so what I'm doing is trying to sort of bridge that gap, especially because we have a lot of very exciting, strong gravity experiments and observations, right? So we have gravitational wave physics, which is very new. We have black hole imaging, which is very new. And so you can ask yourself, okay, these things are telling us, these observations or experiments are telling us a lot about black holes, right? We're going to be able to probe the near horizon, right near the black hole region of space-time, like never before in coming years. And so if string theory is correct, can it give us predictions that we might see in these experiments that would actually be sort of a smoking gun of string theory being the true theory of quantum gravity? I think that's a very exciting question, and so my research is basically all around that question, right? Trying to understand, okay, so that's a whole chain of reasoning, right? You have to start with, okay, what is actually a string theory model for a black hole? How do black holes work in string theory? That's a very non-trivial question, a very hard question. And then you need to go further and you say, okay, if I have some kind of black hole model in string theory, how would that model translate into actual things that I can go and observe with my gravitational waves or my black hole imaging? So that's the second step. That's also a very hard thing to actually get some insights from.
So like you just said, like your research focuses on black holes and gravitational
Mhm.
waves. So like what about these topics makes it so exciting to study?
Well, black holes have always been sort of mysterious objects, right? So I think the first the understanding of black holes is something that was a very gradual thing in history, right? So in 1916, I believe it was, Schwarzschild, wrote down the first solution in general relativity that, we now understand represents a black hole, but it took like 50 years before people really understood what was going on. Um, and yeah, so I think it was, the 50s and 60s that people started understanding, okay, black holes are really a thing, right? They are really an object that exists, right? They're not just some weird math artifact in the theory of general relativity. But then there were a lot of mysteries, right? Like, okay, so you enter a black hole, but then you can't get out again. Okay, and then people started thinking, and they realized that Hawking realized that black holes actually do have to evaporate, so stuff does come out of the black hole. But then there's all kinds of problems like, well, wait, if I have information, how does that go in the black hole and then come out again, or does it not, right? Because we expect that information isn't lost in physics. In principle, if I know where all of the particles in the universe are right now, then I could predict the rest of the universe, the rest of the life of the universe exactly in principle. But it seemed like, if you throw something into a black hole, like if I create a black hole by, colliding a bunch of elephants, or I created by colliding a bunch of giraffes, I'm going to get the same black hole in the end. And I've kind of lost the information, or I can never get the information out of it anymore. Like, was it elephants or was it giraffes that went into the black hole? And so this is what's called the information paradox, right? Which is like a very famous paradox or mystery or problem with black hole physics. And so these things, came up with Hawking and others, decades ago, and have sort of remained problems since, right? There's still sort of open questions in theoretical physics. And so I think from a theoretical point of view, at least, that's why they're so interesting, right? Is because there's just a lot of problems with them still. They're sort of the ideal sandbox or playground for theoretical physicists to get more understanding about these fundamental things about gravity, right? We just don't understand how gravity works in a black hole. I think that's fair to say. And from the observational point of view, they're just very elusive, right? They're like their name suggests, they're black. So, good luck finding them with a telescope, right? The only way we can really observe them is sort of by observing their environment. So black hole imaging, I said something about that. We have pictures of black holes since 2019. The Event Horizon Telescope took the first pictures of black holes, but it's not really a picture of a black hole. It's a picture of the stuff around a black hole, right? Because a black hole itself you can't see. And so now with gravitational waves, I think it's very exciting that instead of just seeing the effects of black holes, what they do to the stuff around them, we're really kind of hearing, I should say, with gravitational waves, not seeing, but hearing these gravitational waves coming from the black holes themselves, and it's showing us a lot more black holes than we could ever see with telescopes. So I think from both points of view, theoretical and observational, black holes are just very, very interesting, but very ill understood objects that, hopefully we're sort of on the cusp of understanding better now.
So, what do you think is a misconception about black holes, like commonly known today?
Um, a misconception. Well, I guess there's a bunch of things because black holes are very difficult. I think, well, one misconception is that, we understand what's going on with black holes. Um, and sometimes I think people, well, I guess one misconception could be that, black holes are really black and nothing can come out. Because Hawking showed that, if you take quantum mechanics seriously, then actually black holes are radiating all the time. They're radiating thermally, which means with a given temperature, kind of like a hot piece of coal, if you will, right, is radiating like black body radiation. And its temperature is very low, so it's very, very little bit of emission, but it's still there. So that's one misconception. Um, Another misconception that I've seen in people who sort of read a little bit about it, but are sort of, but understandably not don't have time or whatever to go into depth, is you hear things like, oh, but time slows down as you approach the black hole and you never actually enter the black hole, these kind of concepts. And so that's, you know, it's very dependent on the point of view. So who is observing? And that's something that's very hard to wrap your head around in general relativity. But someone standing very far away from the black hole will indeed see a spacecraft approach the black hole horizon, but never actually enter it. It will sort of freeze in time. But of course, from the point of view of the spacecraft that's going towards the horizon, right, time is not slowing down from their point of view. It's just going on, and they just pass the horizon in a finite amount of time without any problem. So it's this very, very counterintuitive double kind of point of view that are both correct. But it's important to say who is doing the observing of the freezing in time, and your time doesn't get frozen from your own point of view. That never happens. So maybe those are some good misconceptions.
It's amazing how there's still like so much to learn about our universe and like every like century or every year we're making like new discoveries. So it's always like amazing to think about how people are actually able to make those discoveries.
Absolutely.
So, gravitational waves was one of the most significant discoveries of the century. So why do you think they were so important?
Yeah, so I would say that gravitational waves are, um, so discovery is maybe a strong word, right? So the history of gravitational waves is that in 1916, Einstein was sort of the first one to theoretically predict them for the first time. Now there was a lot of confusion also by Einstein from then until about the 50s or the 60s whether gravitational waves were even in principle real, right? And so by the 50s, people started to understand, okay, they carry energy from one place to the other, and therefore they're real, right? Something that carries energy is a real physical thing that you can measure, right? You can measure the energy being transferred. But then, people only started thinking about actually observing them in the 70s or 60s and 70s. And we only succeeded in 2015, right? Directly, at least. So this was the first direct detection of gravitational waves in 2015 in LIGO in America. And so this is probably what you mean by discovery. And so this was really, I think, a key turning point. I would agree that it's a very important discovery, a very important milestone in physics, because it's as if we were looking at the universe, or it is as if we were looking at the universe with only light, with only one sense, and now suddenly we have another sense. We can hear the universe as well, right? It's very much like that, right? Because there's just think about everyday life, right? There's a lot of things that we can hear but we can't see, or that when we hear them as well as seeing, we get a lot more information and we understand them much better. And it's exactly the same with the universe. In fact, I would say it's even worse with the universe in terms of seeing, because only 5% of the universe emits light or reflects light. And so 95% of the universe is well, literally dark, because it's dark matter, dark energy. And so it's invisible for light telescopes. You cannot see it. And so with gravitational waves, we can finally, hear the rest of the universe, and hopefully shed light on, the 95% of the universe that's dark.
I see. So you were involved with the Einstein Telescope project? Okay. So
Mhm.
like what is it and like what new discoveries could it help us make?
Yeah, so I mentioned LIGO, right, in 2015 as
Yeah.
being the first detector to detect gravitational waves. And LIGO, and so also its sisters, let's say Virgo in Italy and Kagra in Japan. These are sort of all of the same generation of detectors. So they're all about the same in, how well they do, how sensitive they are. And it's not a big stretch to say that LIGO's primary mission was basically just to show that we can do it, right? That we can measure gravitational waves. They exist, A, and B, it is possible to measure them. That's sort of what LIGO's mission was, and check, right? We did it. But it's not quite LIGO's mission, or it wasn't LIGO's mission to do, precision science with these gravitational waves yet. It's not that sensitive anymore, right? To put it in sort of distance terms, we're only really listening to our cosmic backyard, as it were. And so we really need the next generation of gravitational wave detectors to take it further, right? To be able to listen to, much more of the universe and to have more precise measurements of the universe. And so the Einstein telescope is one of these proposed next generation detectors, and one that we're, I would say, almost certainly going to build in Europe, but it's not sure yet where. And so at the moment, there's three different candidates regions. So there's the one that I'm attached to, which is to build it here on the three-country region between Belgium, Netherlands, and Germany. There's Sardinia in Italy, the island in Italy, and there's Saxony, which is the east of Germany. And so these three regions are now preparing their bid, preparing their candidature. And then next year, a decision will be made on the European level as to where the Einstein telescope will be built. By the way, since you're in the US, I can mention that the US, well, okay, scientifically, I think there's a big question mark everywhere in the US now, but at least the plan as of a few years ago was that you would also be building a new generation gravitational wave detector called the Cosmic Explorer, which would be roughly the same, be able to do roughly the same physics as the Einstein telescope. And if you have both Einstein telescope and Cosmic Explorer, then you can do really cool things together.
I think I heard about it, but I wasn't too familiar if we're actually doing it or not.
Yeah, I'm not sure what the status is at the moment. I'm not very involved with that, but I hope so.
I hope so. So, what area of space science or physics do you think will experience the most like exciting breakthroughs in the next decade?
Well, I'm definitely biased, but I think gravitational wave physics takes the lead there. Simply because there's just so much that's just open for us now, right? Like I said, LIGO gave us a proof of principle, like we can do it, and this is a new field. It's literally a new sense that we've just turned on, and so in the next decades, especially once we have our new next generation detectors. We're going to be getting so much new information about the universe that we just, it's not like we're just, you know, I shouldn't say just, but it's not like we have a new telescope which, can look a little bit further or a little bit more sharply. No, it's like it's a completely new sense that we're opening for the universe. So I think for sure there's going to be all kinds of breakthroughs and insights coming from there. I should also mention that, besides Einstein Telescope and Cosmic Explorer, we're also going to have um, a space mission that's dedicated to gravitational waves. So gravitational wave detector in space. The reason is because in space you can detect gravitational waves of a different frequency than on Earth. And so once we also have that, which is called LISA, this mission, once we have LISA together with Einstein Telescope and possibly Cosmic Explorer, then we're going to have so much information that, we're just not going to know what to do with it.
So now talking about some questions that like the audience may have. So obviously you already gave one advice, but like if
Mhm.
you were to give like an advice to high school students interested in like physics, astronomy, or like specifically aerospace engineering, what would it be?
So I can certainly not talk about aerospace engineering. I'm very far away from engineering. But so advice is like, what should you do, or how should you approach it, or
Yeah, like how should like students who are focused in it and interested in it, how should they like view it and like
Mhm.
what should they do about it?
Okay. I mean, I think if you're really excited about uh, physics and let's say anything really in physics and broadly speaking, you should totally go for it, right? I think it's by all means pursue your passion. Um, if you're asking for like specific advice on like do's and don'ts, I can say, do read a lot, do try to challenge yourself. If you're already sure that you're very passionate about it, look for, try to go beyond popular science books as well, right? So read obviously these books as well, but try to look for maybe summer schools where you can learn more about physics, or look for um, something that you can do that's at your level, but that challenges you, right? That goes beyond the knowledge um, that you get from school, the typical knowledge. I think, don't feel as if, for example, so something that I do hear a lot, maybe not necessarily from high school students, but more from like their parents, is that they're worried about AI as something that will take away jobs in math or physics. Now, obviously, I think one thing that I think is that everybody who's trying to say, oh, in 5 years this, in 10 years this, has no idea what they're talking about, because nobody knows what they're talking about in that respect, right? 5 years ago, nobody knew, nobody was talking about AI in the way that they are now. So we don't know what the situation is going to be. But what I would say right now is the best strategy is to, use all the tools that you have at your disposal, which also means AI. I don't think shying away from a tool just because it's new and unknown is a good idea, but be very aware of what you're doing, right? So I think one really, really important caveat these days is that a lot of students when they use AI, you notice that they understand less, right? There's a lot of thinking, oh, but I can just use AI and then I can sort of skip ahead, or I can do things that I couldn't do without it, and that's certainly true. But the struggle is important, right? Struggling is really important. I think that's something that is not understood or appreciated as much, right? You don't sit through tedious computations by hand, when you're studying, because it's fun or because it actually adds to knowledge because it's a computation that a million people have done before you. You do it to train yourself, you train your mind, to train your skills, and so you should still do that. But now you have sort of more tools at your disposal where you can go, where you can go further, or maybe your AI can help you point in the right direction or whatever, right? But what I've also encountered is high school students who now are, delivering or producing what looks like, research grade papers using AI, which is not a bad thing in itself, but if they're doing it by sort of having half an idea where they don't really have the mathematical meat behind it, and then they feed it into the AI without being able to be critical about it because you just don't have that mathematical background, And then in the end, you get something that looks like a very impressive paper, but when you go into the details, there's not much there, right? Or it's just kind of yeah. So I think that's something to be wary about, right? Don't over trust that it can do stuff for you that you can't. You still need to, people who are using this, like mathematicians or physicists who are using this in their research. I'm also using it in my research. What you do is you use it for inspiration, you use it to do hard calculations, etc. But then you check it, right? But then you check it, then you go through it yourself. It gives you maybe a new idea, but then you still have to do that idea, or you still have to check that idea. It gets dangerous once you just trust it to be like, okay, I don't really know what it's saying, but let's trust it and let's keep going with it, right? So make sure you always understand everything that you use is, I guess, a good advice there.
Yes, I agree. So before we wrap up, I have one final question. So if
Sure.
you could like instantly learn the answer to one mystery of the universe, what would it be?
Well, I mean, I would say I would like to know the theory of everything, or, if maybe a little more specific, I want to know what the um, ultimate quantum theory of gravity is. Is it string theory? Is it not string theory? That would be, I think, an amazing insight to know.
That would be cool, yeah. This
Hmm.
has been such like a fascinating conversation. I've obviously learned so much about black holes and gravitational waves, and this was a topic that we hear a lot about, but I never really had the opportunity to like learn about it because they don't teach it to us in school and stuff. But it's
Hmm.
really exciting to know all the research that's being done, and I hope all the future projects like make it out and like we actually get the information that we want in the future. So thank you so much for sharing your experiences, insights, and advice with us today. I am sure that the audience will take away great advice and also information that they learned today.
Well, you're very welcome. It was my pleasure.
Thank you so much. Thank you to everyone who joined us for today's episode. I hope you all learned something new and felt just as inspired as I did. Make sure to join me next time for another conversation that inspires curiosity and learning. Till then, explore, engineer, and elevate. See you next time.